At Meta, his work in real-time monitoring of AI training systems has played a very critical role in large language model training. And he's also got a lot of experience as a software engineer at Microsoft. So without further ado, I'm going to hand over now. The audience is yours, and we very much look forward to your talk.
Thanks, Keely. Hey everyone, this is Lalit. I'm a software engineer at Meta. My day-to-day work basically involves building training infrastructure for LLMs. So I'm not a machine learning engineer building the models, but I'm basically building the training infrastructure to train them. As Keely called out, I worked at Microsoft for around 7 years, and then for last 5 years I've been at Meta. Today, I'm really excited to talk to you all about the scaling challenges in LLM training. Yeah, we can begin it here. Just going over the content of this presentation, we'll start with the high-level evolution of LLMs, talking about their journey through the time. Scaling challenges, primarily in training and inferencing. This is mostly around the infrastructure challenges and less about the model development challenge itself. Then we'll talk about some of the innovative training solutions that are being employed nowadays to train these large language models at scale. Then we have some real-world case studies to cover, some work on the future direction in this work stream, and at the end we'll basically end with a Q&A. With that, let's start with the introduction of LLMs. So I think many of you might already have this level of context, but I'll just start from the basics. So what an LLM is? An LLM, or a large language model, is a advanced and very large neural network which is designed to understand, generate, and update human language on large scale. I think ChatGPT is something that kind of brought this concept to most of our lives, but there are several different ones at this point. And I think most of us are kind of getting accustomed to using them in our day-to-day work. I see start including like people working on, people studying in colleges, industry, or anywhere. Like these models has like significantly changed our life. Their key characteristics are basically two things. One is the scale and size, billions of parameters, really large models. And second one is the deep learning architecture. We'll talk about it a little bit in the later section, but these LLMs basically utilizes transformer architecture with self-attention mechanism. That kind of makes it capable of capturing complex language patterns and answer complex queries, and even process large paragraphs as huge as a whole novel as well. So that's what LLMs are. Let's talk about their journey through the time. If we look at like a decade or couple decades back, you will see that in early stages, the language models were mostly statistical models. They predicted words based on a fixed word sequences that were given to them, but their capabilities were very much limited. They could not really understand complex queries or large paragraphs as their input. That's where the journey began, and then we came through RNNs, LSTMs, GRUs, and various models which were kind of subsequent improvement over the previous ones, but they still had their own challenges in terms of not being able to handle long-term dependencies, not being able to handle complex queries in natural language, so their use cases were pretty limited. Same like in last 10 years, we got to slightly better variant of these, word2vec and Glove, but they were also very much limited in their capabilities. And then came this transformer architecture. I think many of us might know about this famous paper from Google, which is attention is all you need. This basically introduced a very different architecture, transformer-based architecture that utilizes self-attention mechanisms. So this kind of changed the game, right? This basically allowed these models to process very complex queries and basically process a very large chunk of data efficiently. So that's where things begin in 2017 when this architecture was first launched by Google. Um, then basically following that, we saw the rise of the pre-trained models. I think most of us kind of learned about large language models through GPT series, GPT 1, 2, and 3. 3 being like a significant bump over the previous generations. And I think that's where everybody in the world kind of started getting a taste of these LLMs. At this point, I think we have beyond GPT-3, we have very advanced models. Some of them are with multimodal capabilities, which can generate text and images. And the size and the performance is just growing. And there's a lot going on in this space every day. If you look at some of these examples, we have some of these models which has parameters in trillions as well, like 1.6 trillion parameters is not rare now. We have a lot of different models. Some of these are offered as closed offerings like GPT. Some of them like Llama are available as open source offering, and we have somewhere in the middle as well. So that's where things are, and this space is very rapidly evolving with the model sizes growing and the performance getting better and better. If we look at this graph, you can see this hockey stick like graph, basically explosive growth in the model sizes and the resource consumption. That's basically the center of our today's discussion around infrastructure challenges in dealing and training with these models. But as you can see, the graph is just exponentially going up in a very short period of time, like from 2019 to 2022 itself. You can see there is like more than 10x growth in size of these models. Talking a little bit more about some of the strengths of LLMs. So what LLMs are really good at? LLMs at its essence are really good at predicting next token in a sentence. And then we leverage that power to do all kind of things with them, right? Um, that's their strength basically. Uh, Now LLMs are not good at everything. Like some of us just using these LLMs through chatbots might be thinking that hey, they are kind of serving all needs and their knowledge is endless, but that's not really true. LLMs knowledge is basically frozen at the time of training, and they can't really answer any questions related to current events or an event that happened after their training by themselves. So for a very simple example, if you ask an LLM, hey, how's the weather in London? By itself, it wouldn't know. It kind of needs to consult an external data source to answer this question for you. Very simple things like what is date today? Even that an LLM wouldn't know until that information is externally fed into it, or it is capable of or running some kind of code to figure that out. So that's basically the limitation as well. This diagram is talking a little bit about what I just explained, that in many cases the knowledge is kind of fed into the LLM through a wrapper. So this diagram is kind of depicting that. Many of us who are not closely involved with the LLM development or training does not know this, but if you but if you try to use a raw LLM through, let's say, OpenAPI APIs, the developer APIs, then you would kind of notice this thing that, hey, there is a wrapper that OpenAI or other developers has kind of built around the LLMs to feed this information into them. Okay, but now coming back to their core strengths, how did LLMs become so good at understanding natural language? I think the answer is simple. First of all, they are large size with the billions of parameters trained with large amount of data. They kind of become really good at understanding natural languages. But both of these things are the key here. One is the size. The second one is the amount of data. And that's where all the challenges in training, maintaining, and running them for inference comes into the picture from. Um, Size is one thing, but I think one of the biggest challenge in training LLMs is the data. The vast amount of data we really need to train them is very important. So historically, for training text models, we used to basically use human labeled data. but as you know, that process is very slow. Even if we employ thousands of people to manually label the data, that will not be able to generate enough sample data for the model to train. It might be a very high quality data, but the amount will just not be sufficient for training at this kind of a scale. So I have a simple example here that you can see. This is basically the basic technique that's being used to train these models. We leverage a lot of open source or licensed data sets available out there, and through some automation we are able to generate some good quality training data for these LLMs. For example, let's say if you have a large corpora of millions of paragraphs or sentences, you pick one of them, let's say this one, the cat sat on the mat. You can, through an automation without any human intervention, you could just mask some words in this sentence and make it like the cat sat on the right, and ask this question to the LLM. Now through the automation itself, you kind of can provide the training input as well as the expected output to the model, and that's how we are able to scale that kind of training for LLM, because for an efficient training we need billions or even trillions of uh, labeled data, which is not really feasible to do it manually. So that's basically the core reason for the development of these LLMs and how they are becoming so good. Um, and at the end, some of this data, there are challenges with this kind of process as well. This data might not be well diverse. It might have outliers. To counter those things, then LLMs are finally fine-tuned with some high-quality manually labeled data, where we have full control on what the LLM sees and what it learns. But for the pre-training, it's very important to have some kind of automation generating the training data for the model. Some research papers also suggest that some of these models are still undertrained. So there is this paper that I linked from DeepMind, Google, and that basically suggests that all of these big models that we have at the moment are mostly undertrained. Their conclusion is that for a model of size X billion parameters, you need like 20x uh, tokens to train it efficiently. So if you look at all of the existing examples, GPT-3, Lambda, all of those doesn't seem to maintain that ratio. At max, you can see like 2x tokens compared to the model size. I think they tried with a 70 billion model and trained it with 20x token, which is 1.4 trillion, and saw some impressive results. So in this case, actually, for a counter argument here is that for GPT-3 to be more effective, instead of further increasing the size of the model, they should look at increasing the number of tokens it gets trained with. But of course, this is like a huge scale, and finding that kind of good quality data is really hard. So that's basically one primary challenge in LLM training. Um, just touching a little bit upon how these models generate images, because I think oftentimes many of us use these models with images as well. So for image generation, the LLMs are generally combined with some image generation models, and the way they are trained is that uh, the text input is received by the model and understood by the model, saying that hey, what it is being asked to generate, and then the model starts basically figuring out how to map those things on the latent space. If you ask a model saying that hey, generate an image of cat sitting on a floor, so it tries to understand the way the input and then starts painting that picture. And how it learns to paint that picture is basically during training, uh, we take a large number of images and feed it into the model repeatedly, every time adding some noise to it, and then the model is kind of learned to recover the image back from the noise. And if you do this process enough times, you would see that at the end, uh, we will have an image with just noise and nothing into it. But through iterative step, the model kind of learns to how to clear that noise and slowly convert it into a picture that it has seen at the time of training. So that's the very high level idea about Generating images, I wouldn't go too much into details around that, but the point here is that even for a generative AI model to generate images efficiently, we really need a large number of images so that it could really learn to generate a vast amount of different characteristics that users might ask it to generate. And you might have seen, and I see this from my personal experience, at this point the image generation models are not as good as the text generation. The reason being the data. The amount of high quality images for training is really hard to find compared to the high quality text that we can find. So getting into the scaling challenges in LLM, which is the primary focus for this talk today. I think the very first one that all of us might be hearing, even if we are not working closely on the LLM space, is the computational demand. We all know how NVIDIA stock has been growing, reason being the demand for the product they build, which is high compute power uh, GPUs, right? So basically that's the fundamental challenge at this point. There has been exponential growth in the model size. We just saw how the models has grown from millions to hundreds of billions to even trillions of parameters at this point. And we really need a lot amount of compute power to efficiently train these models. A lot of companies has existing infrastructures that was using CPU training. All of those CPU infrastructure is kind of getting obsolete because CPUs definitely can't handle these large models. We do need GPUs, and in GPUs also we have like varying capability of GPUs. The Some of the cutting edge NVIDIA GPUs like H100, 200, and the series are being like the very quick ones, but they are not really available in abundance, and they are very expensive as well. So that's basically a very first fundamental challenge. Building first of all, we need to acquire a very large number of these GPUs. Nowadays, I think some of the LLM trainings are also leveraging up to hundreds of thousands of GPUs. So acquiring those many computation resources and then running them at this scale is like a very hard challenge to solve. Moving on to the next one, computation power is one thing. Secondly, we also need to think about the memory and storage requirements. As the model weights are growing, the number of parameters are growing, it takes a lot of memory to load these models and these parameters in memory. It takes a lot of storage space to store these large models, checkpoints, and then load them back while training. Similarly, when you are training with hundreds of thousands of GPUs, you need uh, network communication between them, and the data transfer becomes often bottleneck in transferring data between them. So that kind of introduces delays in fetching that data and really running this training at scale. Checkpoint sizes, I already covered this one. So like the checkpoints are also with you every n steps of the training, we store the model checkpoints in storage. Storage is generally cheap, but writing and reading from the storage kind of adds a lot of IO overhead. And while we are checkpointing the model, the GPUs are just waiting, and we are wasting the computation power. Energy consumption and cost. This is one of the largest blocker for large scale training because just running these many GPUs requires a large amount of power. These GPUs generates a large amount of heat, so we need data centers with like cooling systems to manage this heat. So overall, the energy demand for these systems is really high. Environmental impact, of course, if we are using that much energy to do something that has its own carbon footprints. Financial cost, I have some of these tentative numbers here just to put things in perspective, but of course these numbers are not official as the cost varies depending on the contract between the manufacturer and the buyer. But at high level, you can see that one NVIDIA H100 GPU cost around $30,000 to $40,000, and if you are building a training cluster with 100,000 of these GPUs, it's gonna cost you $3 to $4 billion just for the GPUs. And then on top of that, you need um, the extra cost for the cooling systems, the power systems, and all the people who are managing the data center. So this is huge and not really accessible for smaller organizations to be able to do this. Training stability issues. This is something like as training infra engineers we face daily in our day-to-day work. Even if you have a good training cluster built with as many GPUs as you want and the data center is working, you have everything in place, you often see training instability. Reason being that if one of the GPU fails, then you have to restart the training, you have to go back to the previous checkpoint, and the progress that you might have made recently might get lost. There are very innovative solutions. I think the infra engineers are building nowadays, dividing the training into different groups, subgroups, so that we don't have to do restarts across the board. But there is a lot that needs to be done here, and it's just that the infra is not able to catch up to the growing need and the size of these models. That's the basic challenge at this point. For machine learning engineers, there are a lot of challenges that comes in the form of hyperparameter tuning, because there are just so many of them. So if something goes wrong, it takes a really long time to kind of figure out what went wrong, what needs to be tuned, so we can converge the model towards the right output. If the model is not really converging, like you are really wasting a lot of resources while you kind of figure it out. And debugging is a biggest challenge. One core problem with these models is because of their sheer size, you don't really know if they are doing something, why they are doing that. If they are producing a certain output, if they got a bias, it's really hard to figure out where they got it from or how to eliminate those. So as the size is growing, all of these challenges are just becoming harder and harder. That was mostly around training, but you can think of training as like a one-time thing, and then in theory we can say that, hey, probably worth paying that one-time cost, it's probably okay. But it's not just about the training. The inference is also very expensive for these large language models. Generally we debate, hey, probably these LLMs will kill search completely, but if we look at it, search is very cheap compared to the LLM inference. An LLM inference costs quite a bit because the input that's provided by the user has to go through all of these model layers, and a lot of computation power is needed just to run inference on every query. I put some numbers here to put things in perspective, and these numbers might just look small, but remember, things adds up over time uh, when you are basically working with a model. Let's say you are asking it to prepare a presentation for you. It's not just the one query that you will pass it to. You will interact with the model several times. You wouldn't like the some of the outputs, so you would modify your query, ask it again. So if you interact for one presentation, like if you interact with the model 50 to 100 times, and if your tokens are larger, the cost is going to add up. And it's not like OpenAI is making a ton of money by this kind of pricing model. They are paying a lot of price for the amount of GPU and GPUs they have to employ to run inference on these models. Uh, that was primarily around the general challenges we face with the training and inferencing. There are some innovative training solutions that we are using nowadays uh, to get around these challenges. But remember that this thing is like very cutting edge, and we are facing new challenges every day, which is just kind of undermining the work that and the progress that we have made so far. But I'll cover some of them. The first one being the model and data parallelism. So at this scale, you can really see that sequentially training is not an option. We need parallelism, and parallelism might come in different forms. You could use model parallelism or data parallelism, or generally a combination of both. If you are using model parallelism, it's basically splitting the model across multiple devices, and this is kind of becoming imminent nowadays because of the size. It's just not feasible to fit the model on one device at all. So the models are being split onto multiple devices, but that brings it, and that kind of helps us scale the training process, but brings its own challenges in synchronizing the model across all of these devices. The second one is the data parallelism, which is where you kind of just replicate the entire model on each devices and uh, kind of shard your data into different batches fed into each of these devices. This is of course needed, but alone might not be sufficient as the model size is growing. So we generally need a combination of both. And then that brings basically the challenges of how do you synchronize the state? How do you checkpoint across multiple of these hardwares? If one of these hardware fails, then how do you minimize the restart and the impact on the entire training? So there is a lot of work, cutting edge work that's going on this front to kind of deal with some of these challenges and build these techniques to unblock these LLM training. Besides compute, I think one more bigger problem is how do you efficiently handle your data? If some of you might who are closer to infra might have been using this term SM utilization on NVIDIA GPUs, which is basically in simple terms, it's the capability to be able to use the computation power from from NVIDIA GPUs efficiently. These NVIDIA GPUs are really powerful, and they can really handle a lot of arithmetic operations. But one bigger challenge is that but we often see the SM utilization being low. That means we are often not really using them as efficiently as we should. Reason being that there are limitations in terms of how fast we could feed the data for into these GPUs so that they can efficiently use that data. There are several constraints, several places where we get constrained, like the network bandwidth, how fast we can load the data, and then the memory constraint, how much data can we load and at what pace. So this is one of the bigger challenge that NVIDIA itself and a lot of infra researchers are working on, how to improve this SM utilization so we can more efficiently use the computation power that's there in these GPUs. Some of the techniques that people are employing nowadays is asynchronous data loading, where we basically uh, load a lot of data for the next batch that the model is going to run on, and to just keep the GPU utilization high and reduce the wait time for loading the data. But again, we'll be constrained by how much additional data we can hold in memory, and how much data we can transfer over the wire when there are like thousands and hundreds of thousands of these guys are running in parallel. Prefetching, caching, all of these techniques are similar, just trying to make sure that we can feed the data at faster pace into these GPUs. There is a lot of work going on optimizing the data formats so that this data can be compressed and efficiently stored in memory and on the storage layer so that we can efficiently process them. Next one is multi data center training. As you see the number of GPUs we are using in training, and the amount of infrastructure requirement, the power requirement is just exponentially growing, and it's kind of becoming impossible to just train these models in a single data center. So not a lot of people have done this at a scale yet, but I think the direction where things are moving is leveraging multiple data centers for training one model. This definitely comes with a lot of challenges because if these data centers are physically apart, it's really hard to train a single model across both of them. But it does come off with a lot of benefits because if your data centers are geographically distributed, the power resource requirement and all of the resources available globally can be leveraged together to train one model. And it comes with some good things as well related to compliance, like you don't have to physically move the data in some cases where it's not even possible. So it comes with all of those benefits. but it has a lot of challenges, and I don't think anybody has done this at large scale yet. The network latency and bandwidth is very uh, big bottleneck in this case when you are transferring data even just between like US East and West Coast. The SM utilization that we were talking about previously is probably gonna go down further because it will take time to synchronize the state between GPUs running on the East Coast and the West Coast of the US if you are training a model like that. There are a lot of other challenges that comes in like data consistency. How do you make sure that the model parameters are consistent across the um, region uh, in terms of cost managements? Even though we will be able to leverage the global resources, there will still be a lot of cost for transferring the data, and based on the region the pricing might vary. There is security risk as well because when the data is in flight, it's in transit, then you need to make sure that the data is secure and it is not compromised. So a lot of new challenges kind of comes in, but this is a very uh, cutting edge area where a lot of people are invested in, and it's kind of becoming imminent that the next generation of models will definitely be requiring multiple data centers for a single model training. Uh, Other techniques that we talked about so far are primarily around the infrastructure optimizations. Just shifting gears a little bit and talking about some of the areas where things can be optimized at the model level itself. And as we talked earlier, the model training is not just one time job. You have to run inferences on that model. That's also expensive. So given all of that, I think it's also very important to kind of optimize the model itself and make sure that you have you are using the right or the appropriate model for the use case. In many cases, we are looking at techniques like knowledge distillation because you might have started with a model which is like 400 billion parameters, a lot capable in a lot of sense, but you might really not need that for every use case. And running such a large model for every use case is gonna be really expensive. So we are looking at things like how do we distill the knowledge from the model, make it compress it, make it shorter so that it can be more efficient. There are a lot of techniques like teacher student framework that are being used, like where you have a large model, you try to mimic the same behavior with a smaller model with less parameters. That's gonna go a long way every time that model is used for inferencing. Uh, then yeah, but there are some challenges in this space as well because while distilling the knowledge, you have to be very careful, otherwise the performance might degrade. So this is also a very challenging and cutting edge area where a lot of machine learning engineers uh, are kind of doing a lot of experiments trying to figure out how could they find more optimal solutions with smaller models. Let's do a little bit of some real world case studies. Uh, this, I must admit, this is a bit hard because this data is not really officially published by most of the companies. So this is what I gathered from different sources. Uh, but if you look at how the first revolutionary model, we can say GPT 3.0, was trained, I think the number of parameters are official. OpenAI confirmed that it is using 175 billion parameters, and there are some speculations around the rest of this data, so it's not really official. But it is estimated to have been trained with around 300 billion tokens. It used some vast data sets like Common Crawl, online books, Wikipedia data for training. Uh, in terms of GPUs, I think the speculation is that this was trained over several thousand V100 NVIDIA GPUs uh, interconnected with the NVIDIA link for faster communication between the GPUs. So GPT 3.0 was one of the initial large scale training. And that's where I think this is a very good baseline to look at, but things has evolved since then. I don't have numbers for GPT 4.0, but that's a much larger model and must have been trained on much larger data set on a much larger training cluster. Um, or if you look at a model of size GPT 3.0 or bigger, you would notice that with this size of model, you can't really fit it on one device. So the speculation is that OpenAI likely employed model parallelism techniques, of course, data parallelism as well, to train this model. And this model was probably trained for multiple weeks or even months uh, before it came out. So a lot of challenges that we just talked about, GPT must have faced that. It's just that we don't have official data to talk about those things, but that's kind of the scale where things begin, and you can just see that this scale has grown a lot. And today's model, this is a couple years back story. Today's challenges and scale has like quadrupled or more. So talking a little bit about some of the future direction of the work. I think while talking about the challenges, we have been seeing hardware limitations all over the place. The supply of the high performance GPUs is very limited. They are very expensive, and some of those like NVIDIA are expensive and performant, but still there are limitations, like they can do a lot of computation, but memory limitations doesn't allow their usage to them to be utilized at a full scale. Um, that's where I think there is a lot of scope for building specialized AI chips, and we have been reading news about a lot of companies working on their own AI chips, and kind of fixing some of these limitations on the general purpose NVIDIA GPUs. You could, in theory, you could potentially reduce the cost of a GPU by lowering down the compute power, because you know that you won't be, in most cases you are not able to use that kind of compute power because of the limitations around the data speed at which the data can be fed into the GPU. So specialized AI chips, I think, are being researched on a lot, and I think in next few years we'll definitely see a lot more innovation coming along these lines, making things more energy efficient, reducing the overall cost to build these training clusters, which is standing at like $4 to $5 billion at this point. Um, on the model front itself, I think there is a lot of room for software and algorithm improvements, because I think so far there is, you can kind of see a race in terms of the model size, but the exploding model size is just putting a lot of different challenges in terms of training and inference. So there is a good opportunity for machine learning engineers to come up with innovative techniques to develop smaller models that could be that could have same level of capabilities as a larger model, and maybe or maybe using these larger models more efficiently, so that we don't have to further go up in size. Rather, we can optimize things so that they become more efficient with the current size they have. There is a lot of work going on around the efficiency of arithmetic operations itself, because I think in many cases we use 32-bit arithmetic operations for the precision, but that kind of precision might not be needed. So people have started using mixed precision, like 16 to 32-bit, a combination of both. I think there is scope for it to go down even further and optimize the training and efficiency, training and inference efficiency based on that. Uh, Data management, I think one of the primary focus so far has been the model size and the complexity. But as we were talking about the paper from Google, where they were saying that a lot of these models are undertrained. I think there is a lot of work going on in that space as well. And that how do we make sure that these models are adequately trained and optimally trained, so that instead of just increasing the size of the model to gain better performance, we can kind of train them more efficiently, and we can still achieve the similar outcomes with a smaller models. Synthetic data generation is the other thing. I think I briefly mentioned in the beginning that so far we have the automations in place which can scrape a lot of data from the web and generate high quality samples for the model training. but there is more work to do here. And if we can have mechanisms in place to generate this data synthetically and even at larger scale, then we might be able to fix the undertraining problem for these models, and then achieve the better results even with the smaller models. Uh, and ethical and responsible AI, I think this is one hot debated topic. We have seen some initial instances where the model was not behaving as expected, and in some cases we have seen model being biased towards the data that it might have seen during its training. So a lot of effort is being put at this moment to kind of mitigate the bias in these large language models. Uh, One challenge I mentioned previously as well, that there is a lack of transparency in how these models work and how they generate some outputs. Whenever we have to kind of mitigate a risk, it's mostly around in the model wrapper, which is basically adding more guardrails in the model wrapper, tuning some hyperparameters to mitigate some issues that we might be seeing with these models. But today it's really hard to debug and understand why model is exhibiting certain behaviors, or why it is producing certain outputs. So there is a lot of work going on in kind of building some kind of transparency and debugging capabilities into this model to understand when things goes wrong, how to fix them in the right way. And then we have several other challenges our way, like the privacy, responsible AI, making sure that that these AI agents are aiding the humans and not really kind of going in the other direction where they could lead to some bad outcomes. I think that's all I had to share. I think with this, we can probably open up for questions now.
That is fantastic. Thank you so much. If anybody has a question, you can either put it into the chat, or wow, we've got a few questions coming in quickly, and also in the Q&A. So I'm going to start first of all with the one that's just popped in, the Q&A. Can you please elaborate more on self-supervised training? Why self-supervised, and what is the role in large language models?
Yep. Yeah, that's a very good question actually. And that is the fundamental reason for these models to become so great at understanding the natural languages. Basically, in a supervised training, you kind of manually label the data and provide models with the input around, hey, this is the expected, this is the input, this is the expected outcome. That kind of supervised training is not really scalable at the scale these models needs to be trained. On the other side, we have like unsupervised training, where the model basically from learns by itself without the need for a high quality labeled data. So this self-supervised training is somewhere in the middle, where we are able to generate a lot of these high quality training samples through some kind of automation. I think I briefly explained that in between, that we have ways to take these some of the sentences from the training data, mask certain words in those, and then feed it into the model. So that kind of self-supervised, that kind of puts this model training into the self-supervised bucket, where without a human intervention, we are still able to generate a lot of the training data that the model need, and train it at a scale. So that's basically the primary reason how this model became so good at where they are today. And also, just to add, these models are using the transformer architecture, where they're able to maintain a long range of context window. I think Gemini at this point has like 128 characters of context window. So if a high quality input signal is provided, the model kind of maintains that long context window, and then through the transformer architecture, it is able to understand that context and generate the next token in the sequence more effectively than what the smaller models that we have seen in past that were kind of trained with supervised model training technique.
Okay, so I hope that question was answered. Oh, there's another one. Before I go on to the second question that's come in, there are a couple of people in the chat who have just asked, is it possible to share your slides afterwards?
Of course, we share.
Okay, so what we'll do is we will collect them as IEEE Computational Intelligence Society, and should be able to send them out. Okay, so I hope that answers those people in the chat. Okay, next question. Is there a relationship between the self-supervised training and usage of synthetic data for training?
Yeah, actually, synthetic data for training, we can probably think as like the next step of the uh, uh, self-supervised training. Uh, Today, we are still dependent on the data being available before we could prepare it by masking words to generate the training samples. But in an ideal world, if we can have, let's say, some large language models themselves generating completely synthetic data, then that's basically opens up the doors for generating a huge amount of data. For example, like GPT-3 was trained with around 300 billion tokens, because that's the amount of data they could find on web accessible to them. But in future, once we have completely synthetic data, some automations maybe using LLMs itself that can generate trillions and multi-trillion tokens, that's basically will really help train these models more effectively. So we can look at like the synthetic training data is like kind of next step from the of the in the self-supervised training.
Okay, so the person, you'll be able to see these anyway, but the person says, thank you for answering those questions. While anything else is coming in, oh, okay, we've got one coming in the chat. What is the maximum size of the data set? I'm not sure what that refers to. So if you want to elaborate anything else in the chat about that question, or do you think you can answer it?
Yeah, I'm guessing this means like the large amount, oh, like maybe the amount of data these models might have used. Uh, so that is hard to answer actually, because that number is not made public by these companies. Even the numbers that I was sharing, if we go back to this slide, this is from a research paper in from Google, which says these were the number of training tokens these models have used, but this is still not an official number through these companies. OpenAI or nobody is publishing these numbers. So at this point, the speculation is that we have gone to in most trainings we have gone to like 300 400 billion tokens, and the paper published by Google suggests that they were able to train with 1.4 trillion token. So this is probably what we have seen max, but in some cases we might have surpassed this number. It's just that this is not officially available anywhere.
Okay, does that answer the question from the person who posed it? If not, please feel free to add more. I'm just going to add a question. So I really do a lot of work in responsible and ethical AI. You talked a little bit, bias is something that's really always been known in the field of LLMs, and there was a paper out recently which talked about how you can engineer your prompts to try and reduce the amount of bias. Do you think it should be on the prompt engineers who do that, or do you think there is strategies that you could actually impose in that model?
Yeah, I think it's probably needs to be handled both ways. Uh, in pre-training itself, I think it's very important for the model to see diversity of data, because if the model hasn't seen enough diversity in its training data, it's bound to be biased. Uh, with prompt, I think the prompt would kind of be the second layer of defense, where we can ensure through prompt engineering that we probably add maybe we can, through prompt engineering we can modify the prompts or feed additional context through the prompts. So that would like be like a second layer of defense, but the very first layer I think has to be still in the training data itself, and we do need a wide variety and diversity of data, otherwise the model wouldn't just perform well. Through prompt engineering, we can control some of these things, but then the model performance on the data that it has not seen before is likely to deter. So that's kind of the trade-off. And I think at this point, at least in the industry, I see people are using the combination of both prompt engineering plus diversity of data in training to tackle this problem efficiently.
Okay, I could go on with this, but we have another question that's in there, and this is a real good one. How is it possible to train models with synthetic data generated by the same model without divergence in the outcome?
Yep.
Very good question.
Yeah, that's a very good question actually. So today I'm not aware of anybody employing this technique, and this is kind of a future that I covered it under future direction. But if this technique has to be applied, it wouldn't be through the same model. So it would be like, let's say, if OpenAI is working on GPT-5, they could leverage GPT-4 to generate some of the synthetic data for GPT-5 training, which kind of might become the baseline for that training. Of course, in order for GPT-5 to be better than GPT-4, they need additional data for training, but at least the previous version of the same series or some other models, let's say Anthropic, might aid in that process by providing a baseline of data.
Okay, wow. I love these questions that are coming in. So are you ready for this one? I don't know whether you can see the chat. This is a long one, you see, so you might want to, while I'm reading it out, you might want to just have a look as well. In the context of ethical and responsible AI, we have observed that evidential learning enhances transparency in model design. Can evidential learning be applied to LLMs to help reduce hallucinations?
Yep. Actually, sorry about that, but this is the model architecture itself is not my area of expertise, so I don't have a lot of comment on that side of things. I am basically an infra engineer, mostly involved in the training and inference side of these models, and I think that kind of falls into the model design itself, the neural network design itself.
Okay, so we can't answer that one today, but you never know, hopefully in the future. So sorry about that one. So is there any more last minute questions? I'm just going to quickly have a check. Okay, I won't ask you anything else about bias, but I've just got one last one. And you talked a little bit about explainability, okay, and transparency. Can you shed a little bit more light on that? What
Yep.
methods, techniques do you see
Yep.
being
Yeah.
applicable?
That's a very good question, actually, and that's one of the paramount challenge in the LLM space. When you give it a certain input, if it's not providing favorable output, it's really a hard problem to solve because there are just so many layers and so many parameters, and you don't know which layer or which parameter is kind of not behaving as expected. This is a very under-researched area, but the things that I have started seeing is like intermediate logging, where basically people nowadays started logging some of these metrics like loss from each layer in the model, and basically then looking and then trying to analyze that pattern. If there is a drop in the loss curve at certain state, you might want to start from there, that hey, that particular layer is probably not behaving as expected, and that's where you might need some tuning. It's a very complex problem to solve, but I think with things like intermediate logging, some people are trying to kind of uh, uh, solve this problem and gain some more insights into the model's behavior and how it's working.
Okay, well, thank you very much for that. So I think we're almost done. So what I'm going to do is say thank you very much for coming today and sharing your knowledge. It's much appreciated.
Thank you for
No,
hosting.
thank
This
you
was great.
very much. Um, and sharing your insight in large language models. I'm sure there's much more. It's a topic that's going to continue to be quite hot to talk about. Yeah.
Yeah.
So yeah, thank you very much. And with that, everybody, thank you for joining. We will get the slides, and also this will also be available as well through the IEEE CIS and other locations on IEEE. So thank you very much, everyone, for joining us. Good evening, good night, good morning.
Thank you.
Thank you.
Okay, we're back in practice, Joe Ellen.
Is there just the three of us?
Yeah, I think he signed off.
Okay. I'm really sorry about the slides. I sent him the template, well, about 2 months ago with everything else.
That's
And
okay.
I just couldn't believe there was no logos on the front or his name.
Yeah. So I think what we can do is, I think we can create something and just ask people to fill it in, and maybe that's what you've sent him, which is fine.
Yeah, it's a template. Yeah,
But I
which
almost want to say, like, at the beginning, we might have an advertisement or something for a
yeah,
future one, and then at the end, we would basically we can basically put where it would be posted. So then you don't have to just say we're going to post them. We can actually show people where it will go. We'll say it's on the Resource Center and on the CIS website and YouTube or something like that. Just so it's more specific.
Can I apologize to both of you, because I think at the end of the last one that we did, I think 3 weeks ago, you said exactly that, and just because of the amount of stuff I've got to do, I forgot. So I'm
Keely,
sorry.
it's no problem at all.
Oh, yeah.
So but what we could do is we'll just put it together and we'll give it to you. And then, and also what I think in the future, also, instead of emailing the slides out, we will post them. I mean, it's fine, we could do it. But I would recommend that we post them on the CIS webinars page. And then, the reason for that is that we actually will drive traffic to the page. And then the people who are coming for these specific slides might see another webinar that they were interested, either coming up or one that already happened. And then they might click or get interested in that and then say, oh, wow, maybe I want to get more involved or something like that.
Yeah, no, will do.
Yeah.
Yeah, I think that's the best idea. I've wrote it down again now, so I won't forget.
No problem. Thank you so much. You're awesome. So none of this is all just, these are all just minor little things, but I really, really enjoyed his talk because I thought it wasn't too high level. I think like that, I think the explanation and all the things in there about large language models, I thought it helped me. So.
You see, I think that in CIS, there just isn't really we don't have a lead in this space at all, do we? Yet we should.
Yeah.
And I think that trying to get more people in who can talk about this and know it. But the other big area, and I'm so glad. So I had to give a talk, believe it or not, at a hotel conference. And in it was the head guy who'd flown in from Canada, from Microsoft, talking about quantum AI.
Yeah.
Okay. Oh my gosh, it blew my mind, seriously. And I'm thinking, again, we've got this conference. I don't think it's been approved yet, but this is a massive area that CIS needs to get into. Really big.
I agree. So I
Anyway,
think
sorry.
QAI did get approved, so
I
or
can't
it's
remember.
coming.
There was a lot of things going through.
Yeah.
I'll tell you what confuses me, and this is probably not right. I mean, you might know as a director. So what happens is, I'm on Bernadette's committee, but I'm also on Sheridan's committee. Both are in Confcom. So I tend to see proposals and have to evaluate them from two different angles. Do you see what I mean? At some stage in the process, so sometimes I get a bit confused. That's what I'm saying.
Okay.
Maybe I took too much on this year. But say no more. Right. Oh, okay. Thank you. I will be picking up a new schedule for getting some webinars done in the next few weeks. Be honest with you, I think I'm going to focus on the podcast one, getting the January one and the December one booked in, and then I'll get the January webinar. I'm still waiting. I've got about 3 people, but they're just not coming back to me, so I will chase. Okay.
Yeah, and even again, Keely, on the timing for the podcast, like we could literally record 2 on the same day, right? If we're not, and then we could decide when we want to release them. We just have to set the expectations with the speakers of when we'll release it. So if we wanted to do it once a month, but if it was efficient or the time worked for someone, we could do them literally back to back or on whatever really schedule. We don't have to pace them out, but monthly.
Actually more efficient for the company you've got as well, isn't it? Right.
Yeah, I think they're pretty flexible, so that's not the issue. And the other side of that is if you want to be talking about like gosh, a month is like probably a year in terms of the technology space now. So who knows what's going to happen in a month? Maybe we can't hold on to a recording for a month because things that are said might be obsolete in a month.
True, true.
So, okay.
All right. Well, thank you both. Nice
Have a wonderful evening,
nice to
Keely.
see
Thank you so much for your help.
and same to both of you.
Enjoy.
Thank you, Joellen.
Take care.
All
And
right.
happy Halloween. I'm
You
late,
too.
Joellen, but I wanted to tell you.
Did you,
Thank you.
Joellen, did you share your picture with Keely?
No,
Oh.
I didn't. I should.
Yeah, you should.
I'll have to share what I came into the office as.
Cool.
Yeah, I think we're still looking for Noel's heart.
Fantastic.
No problem.
All right.
Take care.
All right,
See you
ladies.
soon.
Have a great night, Keely. Thanks.
Bye.
Bye-bye.